when we discuss invertible matrices, it was important for us whether a square matrix has reduced row echelon form of identity matrix or whether its reduced row echelon form has a zero row. It would be desirable to distinguish such matrices by assigning a number to them. So if the number that we assign to a square matrix is non-zero, then we could say that reduced row echelon form of this matrix is identity. And if a number that's assigned to a square matrix is zero, then this would tell us that its reduced row echelon form has a zero row. And indeed, such a number exists. And so this number is called the determinant of a square matrix. So let's give a definition. So determinant is a function defined on the set of square n by n matrices over a field F, and with values in a field F satisfying the following properties. One, if A, B, and C are three square n by n matrices such that row number I of matrix A is equal to the sum of row number I of matrix B plus row number I of matrix C, and so all other rows are the same. So row J of matrix A is equal to row J of matrix B and is equal to row J of matrix C. So for all J different from I, then determinant of A is equal to the sum of determinant of B plus determinant of C. 2. So if we have two matrices, A and B, and we have that row I of matrix A is equal to C times row I of matrix B, and so all other rows of these two matrices are the same, then determinant of the matrix A is equal to C times determinant of the matrix B. 3. If matrix B is obtained from A by swapping two rows, so we interchange row I and row J, then determinant of A is equal to minus determinant of B. So when we swap two rows, the determinant changes sign. And finally, property 4, that the determinant of the identity matrix is equal to 1. So here, so we define the determinant function by these properties. So what we're going to see is that there is only one function that satisfies these properties. And it's a little bit more difficult to prove that this function actually exists. And so this is what we're going to do later in this course. These properties will allow us to compute the determinants. So for example, property 1 says the following, that if we have a matrix, so we can take an arbitrary row of this matrix and replace it by a sum of 2 rows and keep all other rows unchanged. Then when we split this row in 2, then we will get 2 new matrices. And so property 1 tells us that the determinant of the old matrix is equal to the sum of the 2 determinants. So in this way, we can simplify rows and thus simplify matrices. Likewise, property 2 tells us that if a certain row has a common factor of c, then we can pull this factor out of the determinant. And property 3 says that whenever we need to interchange the order of rows, so this can be done, but we need to be careful, so we need to keep track of the sign. And our goal basically is to take a matrix and to simplify it to the identity matrix, right? So bringing it to reduced row echelon form. And at the end, so we know that determinant of the identity matrix is equal to 1. And so if we just keep track of the changes, like all the factors that we pull out on our way, so then we will be able to compute the determinant of a matrix. Now, these are the defining properties of the determinant. So it will be helpful to use these defining properties to derive some extra additional properties which will also be helpful for us in our computations. The following properties follow from definition. So if matrix A has a 0 row, say row I is equal to 0, so then determinant of A is equal to 0. And indeed, so this follows from the second property. So from 2, so if we have a row of zeros, right, so row I, which is 0, can also be written as 0 times the 0 row, right? So a 0 row has a common factor of 0. And then from this property 2 here, right, so it follows then that determinant of A is equal to 0 times determinant of A, right? So we pull out the factor of 0 and still keep the 0 row there. But 0 times any number is equal to 0. And so this tells us that property 2 implies that the matrix with a row of 0 must have a 0 determinant. In particular, this would imply, as we shall see, that if a reduced row echelon form of a square matrix has a 0 row, then the determinant of such a matrix is also equal to 0. So the next property, which we can call 3 prime, says the following, that if A has 2 equal rows, then determinant of A is equal to 0. And so what we do is, so we swap these 2 rows. So we swap 2 equal rows of A. On one hand, we know that when we swap 2 rows, then the determinant changes sign. But because these 2 rows are equal, then the resulting matrix does not change. So what we get is that this matrix with 2 equal rows will have the property that determinant of A is equal to negative determinant of A. So this is by property 3, right? So we swap 2 equal rows, we get the same matrix, but determinant changes sign. And then, so what we conclude from here is that the determinant of A is equal to 0 Well, strictly speaking, well, if we move this to the left-hand side, right? So we get the 2 times determinant of A is equal to 0. And this implies that determinant of A is equal to 0 unless 2 is equal to 0, right? So this means that unless characteristic of the field is equal to 2. And so what happens here is that if the characteristic of the field is different from 2, then we derive, so we get that if characteristic of f is different from 2, then the property 3 implies property 3 prime. And if characteristic of the field is equal to 2, then 3 does not imply 3 prime. And then, so if characteristic of f is equal to 2, then we should take 3 prime as defining property. So we need to change the definition. So in the case when we work with a field of characteristic 2, like Z2, right? So we should change the definition, and instead of having this property about swapping 2 rows and determinant changing sign, we should say instead that if a matrix has 2 equal rows, then determinant is equal to 0. And we could show that 3 prime actually is stronger than 3, that always 3 prime together with other properties of the determinant implies 3. And I leave this as an exercise. So show that if we replace in the definition of the determinant the property about swapping rows with the property about equal rows, right? So that if 2 rows are equal, then determinant is equal to 0. Then from this we can derive that when we swap 2 rows, then determinant must change sign. So now we're going to see what's the behavior of determinant under elementary row operations. So if we have a matrix A and we apply one elementary row operation and obtain a matrix B, so we would like to find out what's the relation of determinant of B to determinant of A. So this depends on the type of elementary row operation. So if we have type 1, right, so we say row I of the matrix B is equal to row I of the matrix A plus C times row J of the matrix A. So what will happen? So then we can write down in this case that determinant of B, right? So this is determinant of a matrix where we took, so the new row I is equal to row I plus C times row J. And all other rows are unchanged, right? So for example, here we have row J of a matrix A here. So then this equals. So by property 1, so if we have a row of a matrix which is a sum of 2 rows, then we can split the determinant in a sum of 2. So when we split row I in a sum of 2, then the first determinant becomes just determinant of A. And the second determinant becomes the following. So all rows are the same as in matrix A, except for row I is equal to C times row J of the matrix A. And we also have somewhere row J of a matrix A. But now this row has a common factor of C, so we can pull it out. So what we get is we get determinant of A plus a common factor times determinant of a matrix where row I of this new matrix is equal to row J of a matrix A. And row j of this matrix is also equal to row j of the matrix A. So we get a matrix with two equal rows. So this means that this determinant is equal to 0. So we get determinant of A plus C times 0. So we get the answer is determinant of A. And the conclusion is that determinant does not change under elementary row operation of type 1. So if we add to a row a multiple of another row, then determinant does not change. Now, this property 2 tells us how determinant changes when we apply type 2 elementary row operation. So what we see is that if we have type 2, right, so if we multiply a row by a constant, right, so if row number I of B is C times row number I of a matrix A, then this by property 2, so this tells us that determinant of B is C times determinant of A. Right, so here we just wrote it in the other way, right? So here we wrote that the row I of A is C times row I of B, but so this is same thing with A and B swapped. Right, and here, of course, all other rows are the same. So row J of B is equal to row J of A for J different from I. So rather we can say that if a row has a common factor of C, then we can pull out that common factor in front of the determinant. And so then this property 3 tells us the behavior of the determinant under elementary row operations of type 3, right? So when, so for type 3, so when we swap two rows, so determinant of B is equal to negative of determinant of A. So now we see how determinant changes when we apply elementary row operations. So this gives us a strategy for computing the determinant of an arbitrary square matrix. So we start with the matrix, we apply elementary row operations to bring the matrix to row echelon form or reduced row echelon form. And we keep track of the changes of the determinant when we apply elementary row operations. So here we know how determinant changes under each elementary row operation. And then at the end, so we will either get that the reduced row echelon form is the identity matrix. In this case, we will obtain, well, we know the determinant of identity matrix is 1, but we can also accumulate various factors before we reached the identity matrix. And then we get the value of the determinant. Or another possibility is that the reduced row echelon form of a matrix has a 0 row. In this case, we know that determinant of a matrix with a 0 row is equal to 0. So the original matrix will also have a 0 determinant. Let us do a couple of examples to see how this strategy works. So let us compute determinant of the matrix 1, 2, 3, 4. Now, so what we're going to do is we're going to reduce this matrix applying elementary row operations. So the first elementary row operation that we apply is the following. So we say that the new row 2 is row 2 minus 3 times row 1. And so we see that when we apply elementary row operation of type 1, determinant does not change. So the new matrix will have the same determinant. And the new matrix is 1, 2, 0. And here we have 4 minus 6, that's negative 2. Now, here we see that the second row has a common factor of negative 2. We can pull out this factor in front of the determinant. So this becomes negative 2 times determinant of a matrix 1, 2, 0, 1. And now we can bring this to reduced row echelon form by saying that row 1 new is row 1 minus 2 times row 2. And again, the determinant does not change. So we get minus 2 times determinant of the matrix 1, 0, 0, 1. But this is the identity matrix. And we know that the identity matrix has determinant of 1. And so this tells us that the value of the determinant of this matrix is negative 2. Now, if we change this a little bit, right? So if we write down instead determinant of the matrix 1, 2, 3, 6, then applying the same elementary row operation on the first step, so we will get that this determinant is equal to determinant of the matrix 1, 2, 0, 0. So when we apply this elementary row operation, the second row gets erased. And here we get a matrix with a 0 row. So immediately we say that the determinant of this matrix is equal to 0. So we have seen the property that if a matrix has 2 equal rows, then the determinant is equal to 0. So this can be slightly generalized, that if A has 2 proportional rows, then still determinant of A is equal to 0, just like we did here, because when we have 2 proportional rows, we can apply elementary row operation of type 1 to create a 0 row. And so we see that determinant of such a matrix is equal to 0. When we calculate determinants, so sometimes it's more convenient to use a shorter notation. So instead of writing determinant of, say, a matrix 1, 2, 3, 4, so what we do is we write this matrix, but now within straight lines. So these straight lines indicate that we are talking about not a matrix, but the determinant of a matrix. For our next example, let us evaluate the determinant of this 4x4 matrix. So here we see that the first row has a common factor of 2, so which we can pull out. So we get this is equal to 2 times the following determinant. So if we pull out from the first row a factor of 2, we get 1, 0, 2, 2. And then 3 minus 1, 5, 6. And all other rows are unchanged. So we pull out a common factor from one row at a time. So then we can apply elementary row operations of type 1, which do not change the determinant. So here we are going to say that row 2 new is row 2 minus 3 times row 1. Row 3 new is row 3 minus 4 times row 1. And row 4 new is row 4 plus row 1. So these are type 1 elementary row operations, and the determinant does not change. So we get 2 times the following determinant, 1, 0, 2, 2. So we subtract 3 times row 1. So we get 0 minus 1. 5 minus 6, that's negative 1. 6 minus 6, that's 0. Then here we have 4 times row 1. So we get 0, 2. 7 minus 8, negative 1. And 3 minus 8, that's negative 5. And here we add row 1 to the last row. We get 0, 2, 3, negative 3 plus 2, that's negative 1. And 0 plus 2, that's 2. So we see that the second row has a common factor of minus 1. So we can pull it out. So we get negative 2 times the determinant 1, 0, 2, 2 0, 1, 1, 0, 0, 2, negative 1, negative 5, and 0, 2, negative 1, 2. So here we're going to say that row 3 new is row 3 minus 2 times row 2, and row 4 new is row 4 minus 2 times row 2. Since these are type 1 elementary row operations, the determinant does not change. And we get negative 2 times the determinant 1, 0, 2, 2, 0, 1, 1, 0. Then here we get 0, 0. So we have negative 1 minus 2. That's negative 3, negative 5. And 0, 0, negative 3, and 2. So now I'm going to simplify the last row. So I'm going to create 0 here. So we say row 4 new is row 4 minus row 3. And again, the determinant does not change. So minus 2 times the determinant 1, 0, 2, 2, 0, 1, 1, 0, 0, 0, negative 3, negative 5, and 0, 0, 0. So 2 minus negative 5, that's 7. So next, I'm going to pull out a common factor of negative 3 from the third row and the common factor of 7 from the last row. So what we get is now we pick up two factors. So we have negative 2 times negative 3 times 7. And the new matrix is 1, 0, 2, 2, 0, 1, 1, 0, 0, 0, 1, 5/3, and 0, 0, 0, 1. Now, what will be the determinant of this matrix? So now we have what is called upper triangular matrix. So this means that all entries below the diagonal are equal to 0. So, and actually in this matrix, on the diagonal, we have all ones. So now we can apply elementary row operations of type 1. So taking the last row, and we can erase all entries in the last column above the pivot, right? So if we just take, say, row 3 new is row 3 minus 5/3 of row 4, and row 1 new is row 1 minus 2 times row 4. So this will create a 0 here and a 0 here, but the determinant will not change. So after we do this, we can do the same thing with the third pivot. So we can take the third row, so we'll have a 0 here and zeros above the fourth pivot, and subtracted row 3 from the second row and twice row 3 from the last row. So what we actually see here is that when we have an upper triangular matrix with ones on the diagonal, then the determinant of this matrix is equal to the determinant of the identity matrix. So we can erase all entries above the diagonal. And so the determinant of this matrix is equal to 1. And so what we get is that the value of the determinant of the original matrix is equal to the product of these three factors. So here we have 6 times 7, so we get a very nice answer of 42. So this tells us that the determinant of this 4x4 matrix has value 42. So this idea can be generalized to the following, that so we have the following additional property, that the determinant of an upper triangular matrix is the product of its entries on the diagonal. Right, so here we have an upper triangular matrix. So this means that all entries below the diagonal are equal to 0. And so what we claim is that determinants of such a matrix is equal to the product of entries on the diagonal. So in particular, determinant of this matrix is equal to 1 times -3 times 7. So it's -21, right? And multiplying it by -2, we will get our answer. And so the reason to see this is this combination of two ideas. So first, we take the entries on the diagonal and pull them out of each row. And so then we just get the factors in front of the determinant that are equal to the diagonal entries. And then we get ones on the diagonal. And once we have a matrix, upper triangular matrix with ones on the diagonal, we see that its determinant is equal to 1, because now we can use only type 1 elementary row operations to bring this matrix to identity matrix, and determinant of identity matrix is equal to 1. And so because of this, we get this nice property that's good to remember, that once we achieved an upper triangular matrix, then we no longer need to apply elementary row operations, and we can just say what is the value of the determinant by multiplying the entries along the diagonal. So one can see that the same argument actually works for lower triangular matrices. So we can say an upper triangular or a lower triangular. But in these calculations, usually the upper triangular matrices that will come up. But still we have the determinant of a lower triangular matrix is equal to the product of entries on the diagonal. And so here we can do the same thing, only so now instead of erasing entries above the pivots, we'll have to erase entries below the pivots. Another consequence of this discussion is that there exists at most one determinant function. So with the properties that we included in the definition. Right. So here, so basically what this tells us is that we can compute the value of the determinant of any square matrix using this procedure of row reduction. Now, where we have to be careful is that we didn't prove that this procedure is well defined. So this means that a priori it is possible that if we do row reduction in two different ways, so perhaps we could get two different answers. And so this would mean that the determinant function is not well defined and does not exist. So in fact, this is something that we are going to prove later, is that in fact determinant function exists and it is well defined. But proving this will require some extra work that we're not going to do in this lecture. But what we see is that if this function exists, then it's unique, because here we have a procedure for computing it. One way of proving existence of the determinant function is by producing a formula for it. So if we could have an explicit formula for the determinant of a matrix. So currently, we only have a computational procedure, but not a formula. So we can obtain this formula today for matrices of small size. So let us look at 2 by 2 matrices. So let's look at the determinant of a 2 by 2 matrix A, B, C, D. So what I'm going to do first is I'm going to take the first row of this matrix, which is AB, and I'm going to write it as a sum of two rows. So it's a row A0 plus the row 0B. And so then we can use property 1 of the determinant, saying that if we split a row as a sum of two rows, then the determinant of a matrix is the sum of the two determinants. So we conclude that this is the sum of two determinants. It's A0, and then the second row must be unchanged, CD, plus the determinant 0B, CD. Now we do the same for the second row. We write that CD is equal to the sum of two rows, C0 plus 0D. So now we get, this splits into four determinants. We get A0, C0 plus A0, 0D plus 0B, C0 plus 0B, 0D. Next, we pull out common factors. So here we can pull out the common factor of A from the first row and the common factor of C from the second row. So we get A times C times the determinant of matrix 1, 0, 1, 0 plus, so here we pull out factors A and D. So A times D times the determinant of matrix 1, 0, 0, 1 plus B times C times the determinant of a matrix 0, 1, 1, 0 and plus factors B and D times the matrix 0, 1, 0, 1. Now, here, this matrix and the last matrix have equal rows. So this tells us that this determinant is equal to 0 and this determinant is equal to 0. And the determinant of the second matrix is equal to 1 because this is the identity matrix. So what we get is we get A times D. And for this matrix, we should swap these two rows. When we swap these two rows, then the determinant changes sign. So we get minus BC times, if we swap these two rows, we again get the identity matrix. And so this determinant is equal to 1. And the last term is equal to 0, so we're not going to write it down. And so what we get is we get the expression A times D minus B times C. And so this is the determinant, the formula for the determinant of a 2 by 2 matrix. So if we have a matrix A, B, C, D, then its determinant is given by the formula AD minus BC. Now, this formula would show existence of a determinant for 2 by 2 matrices. Because, well, here we have an explicit function that tells us how to calculate the determinant. The only thing that needs to be checked is that this formula, or this function given by this formula, satisfies all the defining properties of the determinant. So let us check, well, at least the first one, right? So suppose we have that row 1 of a matrix A is a sum of row 1 of a matrix B plus row 1 of a matrix C. And row 2s of these three matrices are the same. So we can think that row 1 of matrix A is A3, B3, and it's a sum of two rows, A1, B1, plus A2, B2. So let's verify that in this case, so we need to check that determinant of A in this case is equal to determinant of B plus determinant of C. Now, in this case, we have the following. So A is the matrix A1 plus A2, B1 plus B2, CD. B is the matrix A1, B1, CD. And C is the matrix A2, B2, CD. So by this formula, determinant of A is equal to A1 plus A2 times D minus B1 plus B2 times C. And determinant of B is equal to A1D minus B1C. And determinant of C is equal to A2D minus B2C. And indeed, so we see that this property will hold. So that in this case, so if we add determinant of B plus determinant of C, then clearly we're going to get the expression for determinant of A. So similarly, we can verify the property 2. So if we have a matrix A, which is A, B, C, D, and the matrix B, where we multiply a row by a scalar, then we see that determinant of B is equal to KAD minus KBC, and so this is equal to K times determinant of A. So what we see is that a function given by this expression satisfies property 1 and 2. So this means that if we split one of the rows into sum of two rows, then we get the sum of two determinants. And if we have a common factor in a row, we can pull this common factor out. By the way, these two properties are called in the following way. So we say that determinant is a multilinear function. So this means that the determinant function is linear in each row. So if we take one row and represent it by a sum, then the value of the determinant is the sum of the two determinants. And if in one row we have a common factor, we can pull this common factor out. So for property 3, so if we swap two rows, so suppose B is the matrix where we take A and swap first two rows. So we have CD, AB. Then, so what's determinant of B? So this is C times B minus A times D. And that's equal to negative of determinant of A, which is so negative of A, B, C, D. Right. So we see that property 3 holds. So when we swap two rows of a 2 by 2 matrix, then the value of this function changes sign. And so lastly, we have normalization, is that if we have determinant of I of the identity matrix, so it's a determinant of a matrix 1, 0, 0, 1, by this formula, so it's 1 times 1 minus 0 times 0. So the value of the determinant of identity matrix by this formula is equal to 1. So this tells us that indeed, so a function given by this formula satisfies the defining properties of a determinant for 2 by 2 matrices. So this shows the existence of a determinant function for 2 by 2 matrices. And our procedure, computational procedure, that tells us that we know how to calculate the determinant of each matrix, and actually this computation that we have carried out to derive this formula, so this also shows that determinant function is unique for 2 by 2 matrices. So the same is true for any square matrix. So for any n by n matrix, there exists a well-defined determinant function, but we will need to work harder to prove this fact. We point out that determinants are defined only for square matrices. For non-square rectangular matrices, determinant is not defined. We have to be careful when we pull out common factors out of a matrix. So let's look at the following example. So suppose we have a matrix Ka, Kb, Kc, Kd. So we have a common factor of k in the whole matrix. Then this is equal to k squared times determinant of the matrix A, B, C, D. Because here we pull out a factor of k from the first row and the factor of k from the second row. And so these two factors will multiply, and so it will give us a factor of k squared. So we have to be careful. This idea of a common factor works for each row independently. I find it useful to think about this formula as the following pictogram. So suppose we have a determinant of a 2 by 2 matrix. And so let us visualize this 2 by 2 matrix in this way. Then we say that this determinant is equal to this product minus this product. Right? So we take AD minus BC. And so we can think of this as a pictogram in the following way. So then this idea can be generalized to 3 by 3 matrices. So if we have a 3 by 3 matrix, then its determinant can be represented by the following pictogram. So we have 9 entries in a 3 by 3 matrix. And so then we take the following products. So we take the diagonal. Right, so this is one term in this pictogram. So then we have another term that will be this product. And one more term, which is this product. So these three products will represent the positive terms, and then we will have negative terms, which will be the opposite diagonal, so this product, times the product of 3 entries here, and finally the product of the 3 entries here. So this will be a pictogram for a determinant of a 3 by 3 matrix. It has 6 terms, so 3 terms are triple products with positive signs, and 3 terms are triple products with negative signs. And so an exercise, so derive a formula for a 3 by 3 determinant. So using the same way as we derived this formula for 2 by 2 determinant. So this means that take the first row, like A, B, C, and split it into the sum of 3 rows, A0, 0, 0B, 0, plus 0, 0, C, and so on. And so if we do this kind of calculation, then we will obtain this formula that's represented by these pictograms. Now let us see how this works. So suppose we have a matrix 1, 2, 3, 2, 5, 4, minus 1, 7, and 6. So then the 3 terms corresponding to this part of the pictogram will be 1 times 5 times 6 plus, so the term that corresponds to this triangle, so negative 1 times 2 times 4, and the term that corresponds to this triangle will be 2 times 3 times 7. And then there will be 3 terms with negative signs. So we have minus, so the opposite diagonal will be minus 1 times 5 times 3. Then we have, so this triangle here will be 2 times 2 times 6, and it comes with a negative sign. And one more triangle will be 1 times 7 times 4, and again with negative sign. And so if we evaluate this, so here we get 30 minus 8 and plus 42. So here we get plus 15 minus 24 and minus 28. So what is this? So the positive terms, so 72, 87 minus, and the negative terms 8 minus 24, that's 32, and 28, that's 60. So we get 87 minus 60, so the value of this determinant is 27. Eventually, we'll have more methods, alternative methods for computing determinants, and the point is that you should know all of them. So all methods for computing determinants are useful in different situations, and so all these methods should be known. Now, for 2x2 matrices and 3x3 matrices, now we have 2 ways to compute determinants. So we have a formula, or we have a computational procedure. So when we deal with larger matrices, for 4x4 or larger, then there is a formula for the determinants of such matrices as well, but that formula becomes not practical. It would have still great theoretical importance, but practically for larger matrices than 3x3, we don't use the formula, but we use computational procedure. So the computational procedure that we used is the main method for computing determinants of large matrices. For small matrices, for 2x2 matrices and 3x3 matrices, it is practical to use a formula. So now we see that the determinant distinguishes matrices whose reduced row echelon form is identity matrix. So the determinant of such a matrix will be non-zero, versus matrices whose reduced row echelon form has a row of zeros. For such matrices, the determinant is equal to 0. So let's introduce a piece of terminology. A square matrix is called non-degenerate if its reduced row echelon form is the identity matrix. So otherwise, it is called degenerate. So now we are going to state a big theorem that describes non-degenerate matrices. No part of this theorem is actually new, so we have already discussed all parts of this theorem individually, but now it will be assembled all together in one place. Theorem. Let A be a square n by n matrix. So the following conditions are equivalent. One, reduced row echelon form of A is identity matrix. 2, a system AX equals B is consistent for every B in Fn. 3, a system AX is equal to 0 has a unique solution x is equal to 0. 4, columns of A are linearly independent. 5, columns of A span Fn. 6, columns of A form a basis of Fn. 7, so the same for the rows. So rows of A are linearly independent. 8, rows of A span Fn. 9, rows of A form a basis of Fn. 10, rank of A is equal to n. Let T be a linear transformation from Fn to Fn with matrix A. So then we have properties. So 11, T is surjective. 12, T is injective. 13, T is bijective. 14, T is invertible. 15, A inverse exists. So A is an invertible matrix. 16 is that determinant of A is not equal to 0. And 17 is that the transpose of A is non-degenerate. So this means that reduced row echelon form of A transpose is identity. This theorem is a summary of what we have done in this course. So we already proved the equivalence of all parts of this theorem. So they are all equivalent to the fact that reduced row echelon form of a square matrix is the identity matrix. This concludes the first half of linear algebra. And in the second half, in the continuation, we will discuss further properties of the determinants. We will talk about diagonalization of matrices and eigenvectors and eigenvalues. And we will conclude this course with the Jordan normal form theorem.